Information entropy. In information theory, the entropy, also called the Shannon entropy, of a random variable x can be viewed as the average amount of information contained within each value of x. In mathematical parlance, the average, as used here, refers to the expected value. Notation. Since the letter E was already in use to represent the expected value of a random variable, the uppercase variant of the Greek letter eta, which is H, was chosen to represent entropy. Given a discrete random variable x with n possible values, x1, x2, up to xn, and associated probabilities p1, p2, up to pn, the entropy h of the random variable x is defined as h of x is equal to the expected value of I of x, which is equal to the following finite sum, where I of x sub I, which is equal to log base 2 of 1 over p sub I, is classically interpreted as the amount of information received when learning that x has taken on the value x sub I. In other words, the entropy of a random variable is simply a weighted sum, where the amount of information received for each value of x is weighted by the probability that x takes on that value. Example 1, coin toss. Let x be a random variable that takes on value x sub I with probability p sub I. We see that the information content of knowing that the outcome is heads is equal to log base 2 of 1 divided by 0.5, which is equal to 1. The same holds true for the information content in knowing that the outcome is tails. Constructing our finite sum, we obtain the entropy of the random variable x and find it to be 0.5 plus 0.5, which is equal to 1 bit. The above calculations reveal a general property of the expected value function e. The expected value of equally likely outcomes is equal to the arithmetic average of the outcomes. Consequently, we should not be surprised that the entropy of x, in this case, is equal to the information content of any one of the outcomes, i.e. values, of x. For future use, we generalize and document the above results. Equally likely outcomes. Let x be a random variable consisting of equally likely outcomes, each having probability p. The entropy of x can be calculated as follows: log base 2 of 1 divided by p. Example 2. Weighted coin toss. Let y be a random variable for the outcomes of a weighted coin toss, where the probability of heads is 0.75 and the probability of tails is 0.25 for each toss. The information content for each of these two possible outcomes will be 0.415 for heads and 2 for tails. Consequently, our weighted average leads to an entropy calculation of the following: 0.31 plus 0.5, which is equal to 0.81 bits. Example 3, card selection. Given a deck of 52 cards, let x be a random variable that takes on values x sub I with probability p sub I, as listed below. The entropy of the random variable x is therefore 0.5 plus 0.5 plus 0.5, which yields 1.5 bits. This means that the average amount of information received when learning the value of x is 1.5 bits. In the next 3 sections, we drill down to what information entropy is actually telling us. We will consider 3 interpretations of entropy and then specify which meaning of entropy will be of most value to us. I should emphasize, however, that each of the interpretations we will consider will broaden and deepen our understanding of information entropy of a random variable, enabling us to more effectively apply this powerful concept.